Hello there, Mr. Sutton here, bringing you the BC Calculus 7-2 Part 1 homework solutions on Maclaurin series. For number 1, f is a function and has derivatives given by the following information here, along with f of 0. We want to write the third order Taylor polynomial for f at x equals 0 and use it to approximate f of 0.2. So general formula for a zero-based Taylor polynomial, we've got f of 0 plus f prime of 0 times x plus f double prime of 0, x squared over 2 factorial, or just 2. And then we have f triple prime of 0 times x cubed over 3 factorial, something in this form. So we're just going to go through term by term and complete this with the information they gave us. And then we'll plug in 0.2 to that polynomial that we end up with. So for f of 0, we have 4. For f prime of 0, they gave us 5, so that's 5x. For f double prime of 0, we had negative 8, so that's negative 8 divided by 2, or negative 4x squared. And then finally, we had 6 for f triple prime of 0. 3 factorial is also 6, so 6 over 6 cancels, and we just end up with x cubed as our cubic term. All right, let's plug in 0.2 for all of these now and use our calculator to see what that comes out to. And notice that I'm saying f of 0.2 is approximately equal to all this because this is an approximation. It's just a cutoff polynomial here. So plug in all that stuff that was down here in my calculator. We end up with 4.848. Hey, it's even 3 decimals, and it's an exact answer. Nice. On this problem, they're telling us f is a function such that f of 0 is 1, f prime is 2, and f double prime at 0 is negative 2. We want to know which of the following could be the graph of the second degree polynomial for f about x equals 1. So just by looking at the function values here, I mean, we have to have a y-intercept of 1, which all the graphs have. We need a positive slope at 0, which all the graphs have. But now this last one here, the concavity is negative, so we know we're concave down at x equals 0. So that narrows it down to choices A and B. C does not have any kind of concavity going on, that's a line, and D, that's concave up. But in order to pick between A and B, we actually need to know what this Taylor polynomial looks like algebraically. So let's put it together. So we're going to have p of x, I'll say p sub 2 of x equals f of 0, that's 1, plus f prime of 0 times x, so that's 2x, plus f double prime of 0 over 2 factorial, x squared. So that's going to be negative 2 over 2 factorial x squared, just using our Taylor formula here. All right, well, I can simplify this to just x squared over there. But now, at this point, I have to graph this thing. It's an upside-down parabola, I know that. That doesn't really narrow it down. I mean, A looks more parabola-ish, but B may have just gotten cut off. So let's actually graph this out. So there's my polynomial I'm going to graph. And I'm going to go to window, and I'm going to go between negative and positive 1, because that's the window in all of these answer choices. And let me just zoom 0 that, zoom fit. So there's the picture of what this thing looks like between negative 1 and positive 1. And that definitely looks, I'll just display it here, a lot more like choice B than it does like choice A. So we're going with choice B. On this problem, they want us to find the third order Taylor polynomial for this function at x equals 0, so in other words, the Maclaurin series, and use it to approximate the value of our function at 0.8. So let's go ahead and write out the general format for this thing. Using our Taylor polynomial formula, this is going to come out to approximately f of 0 plus f prime of 0 times x, and then we have f double prime over 2 factorial x squared. And then finally, we want third order, so we need f triple prime of 0 x cubed over 3 factorial. And we're just going to cut it off there because we just want, again, third order, so 3 derivatives. All right, let's go ahead and find all of this based off of our function. F of 0, that's just going to be 1 minus 0 to some power. That's just going to be 1. And then f prime is going to be, let's see, take the derivative of this. So this is negative 2 times all that to the negative third power, evaluated at 0. So plugging 0 in here, and we have a tail of negative 1, so that actually becomes positive 2 out in front. So evaluating this with 0 plugged in, that's just essentially 2 times 1, or 2. F double prime now, that's going to be, let's see here, negative 6 times all this to the negative fourth times a tail of negative 1, so it's actually positive 6. And I'm going to call this 3 factorial since we're doing, let's see, basically 3 times 2 times 1. So this is 3 factorial out in front. Evaluated that at 0, we have a value of 3 factorial. And then f triple prime, well, that's going to be, let's see here, negative 4 times 3 factorial times a negative 1, so 4 times all this. That ends up being 4 factorial times all of this to the negative fifth. Evaluate that at 0, and we've essentially just got 4 factorial. Plugging it all back in, we had 1 for f of 0, plus f prime was 2, so 2x, plus we've got 3 factorial x cubed over 2 factorial. But hold on a sec, 3 factorial over 2 factorial is just 3, so 3x squared. And then here we've got 4 factorial over 3 factorial, which is just 4, times x cubed. All we have to do at this point is plug in 0.8 for x. So I'm going to write f of x is approximately p sub 3 of 0.8, which is going to come out to whatever the calculator tells us. So I've plugged my Taylor polynomial in as y1. Quitting out of that, I'll do alpha trace to pull up y1. Now I just have to plug in 0.8 to get an answer of approximately, well actually exactly, 6.568. For number 7, we have the nth derivative of some function at x equals 0 given by this expression here. We want to know which of the following is the Maclaurin series for f. So for Maclaurin series, we need to find a bunch of derivatives and put those next to x's. There's some factorials involved. Let's start by getting some derivatives. All of these answer choices go up to the third power. So these are all third order Taylor polynomials. So let's go ahead and take the first 3 derivatives. Let's start by getting the constant, actually. That's if you plug in 0 for n. So if I plug in 0, that's going to give me just 1 here. We've got 1 over, this all comes out to, let's see, this is 2 times 1, so 2, so 1/2 when all is said and done. And then the first derivative is just all this with 1's plugged in instead. So that's a negative, and we have a 2 over, this is going to be, let's see, 3 times 2 is 6, so this is 1/3 when the dust settles. And then if we plug in 2 for the second derivative, this will become positive. And then we have a 3 over 4 times 4, so 3 over 16. And then finally, our third derivative, this becomes negative out in front. We've got a 4 over 6 times 8. So that actually 5 times 8. So 4 over 10 is going to be 1/10, negative 1/10. Okay, let's start building our polynomial. So starting with our constant term, we can say that f of x equals 1/2, and then we have negative 1/3 times x, and then we have 3 over 16 times x squared over 2 factorial. So I'll write this as 3x squared over 16 times 2 factorial. And then finally we have minus, this will be x to the 4th over 10 times 3 factorial. So the thing you have to be really careful about here is to realize that the quadratic has a 2 factorial and the cubic term has a 3 factorial as part of building this Maclaurin series. So let's go ahead and simplify this because none of the answers have factorials, so they must have simplified. First 2 terms are fine. This next term here, we've really got 3 over 32. And this next term, we've got 1 over 60. So taking a look at our answer choices now, we start with a 1/2. So that gets rid of choice A. Next, we have a negative 1/3, so we're down to B or D. And the next term should be 3 over 32, and then 1 over 60 negative, so choice D is our answer. And just for the sake of actually being mathematically accurate, I'm going to stick a plus ... at the end of these because I said f of x equals, so I'm actually using the entire infinite series there, not just a Taylor polynomial. For number 8, they want us to find the value of f of 3 from a Maclaurin series given by this function here. So if we actually just go ahead and plug in 3, let's see what happens. We end up with this infinite series. Now, not worrying too much about this Maclaurin piece, you might notice that this is a geometric series. We keep multiplying by the same thing over and over again. This is a series with an a1 value of, if we plug in 0 here, this is just 1, and an r value of -3/4. That's what we keep multiplying by. So we can actually use our infinite series sum formula for geometric series. This formula right here, a1 over 1 minus r. Let's just plug in a1 and r and see what this thing comes out to, and that will be f of 3. So we've got 1 over 1 plus 3/4, which is 1 over 7/4, which is, if we just multiply by the reciprocal, 4 over 7. Choice C. For number 9, we need to find the Maclaurin series for this function here, 1 over 1 minus x to the second power. So I'm going to go ahead and start by doing f of 0. That's going to give me 1 over 1, which is just 1. So right away we can eliminate answer choice E because it doesn't start with a 1. Let's keep going now. We'll do f prime. Now if f of x is, if we could write that as 1 minus x to the -2 power, then f prime would be -2 times 1 minus x to the -3 power times a tail of -1 because of this negative x in here. So altogether that is going to be +2 times 1 minus x to the -3rd, which evaluates to +2. Next, let's take our second derivative. So we've got -6, 1 minus x to the -4, times a tail of -1. So that's +6 times 1 minus x to the -4 evaluated at 0. That's going to come out to just 6 because this whole parentheses, again, just becomes 1. So we've got a 6, and then let's go one more derivative. You can see the pattern at this point. We keep multiplying by negative exponent, but the negative keeps getting canceled out by the negative tail that we have here. So our next derivative is going to be 24, 1 minus x to the -5th evaluated at 0, which is just going to come out to 24. Let's go through and write the series now. We can say f of x is equal to 1, plus we've got 2 times x, our first derivative times x, plus we've got 6x squared over 2 factorial, and then we have 24x cubed over 3 factorial. Let's go ahead and simplify this since none of these answer choices have factorials in them. So this expression here, this is really just 6 over 2, which is 3, and this is really 24 over 6, which is 4. So we have 3x squared and 4x cubed, which is kind of cute. That gives us answer choice, let's see here, 1 plus 2x plus, there we go, answer choice C. On this one, we're told that T4 of x is the 4th degree Taylor polynomial for f of x equals x plus 1 quantity to the 5th, about x equals 0. So basically, it's a Maclaurin series. We want to know which of these statements is true. So we have different ways of expressing T4 of x. So we'll have to figure out what T4 of x actually equals. But at least we have some answer choices. So if we don't get any of these, then we know something went wrong. And then we have this idea of, whether our T4 applies a good approximation for f of x at values close to 0 or for all real values of x. So I can tell you right away, since this is a polynomial rather than an entire series, that means it's only going to be good close to the center here, x equals 0, not necessarily all real values. So we can already eliminate the ones that talk about all real values, choices B and D. I mean, that's the whole point of a polynomial, is that you're approximating close to this launching off point. So let's figure out what our polynomial is going to look like. So first we have to start with f of 0, which if I plug 0 in here, that's just going to be 1. Now we need f prime of 0. So f prime of x is going to be 5 times all this stuff to the 4th. Plugging 0 into all of that, that's going to just be 5 times 1, which is just 5. Now for f double prime of 0, we're going to have to go to the 4th derivative because this is a 4th degree Taylor polynomial. So we've got f double prime, that's going to be 20x plus 1 evaluated at 0. And we have a 3rd power up there, so this is going to come out to 20. After that, for f triple prime, we're going to have 60x plus 1 to the 2nd power evaluated at 0. and that's going to come out to 60. So you can see a pattern here. And then finally, the fourth derivative, that's going to be 120x plus 1. Evaluate that at 0, and that comes out to 120. So in general, our pattern is going to be f prime of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared. We're just using our Maclaurin formula here, plus f triple prime of 0 x cubed over 3 factorial. And then finally, we have the fourth derivative of 0, x to the fourth over 4 factorial. Plugging all that stuff in to build our series. F of 0 we said was 1. And now we have f prime of 0, which was 5, times an x, so 5x. And now we have f double prime of 0, that's 20. So we have 20 over 2, basically, which is going to give us 10, so 10x squared. And you'll notice that in these answer choices, these are all simplified. So we're going to simplify down here so we can match something. And already, I mean, we could keep going, but you can clearly see we're going to be matching either choices A or B. And since we said B was already gone because it was talking about all real values of x, choice A is looking pretty good. But let's just finish this out. We've already come this far, right? So f triple prime, that was 60, divided by 3 factorial. That's really 60 over 6, which is going to be 10. And we have that x cubed that is there still. And finally, our fourth derivative of 0, that's 120. 4 factorial, that's going to be 24. So that comes out to 5x to the fourth. And as we said, this is only going to be accurate close to 0 because that was the value at which you found all these derivatives. So all bets are off the further out you move from 0. So that then means we're going to have answer choice A. On this problem, I have this function f with derivatives of all orders, and we have some information about the value of f and its first 3 derivatives at 0. Then they're telling us the g function is given by the integral from 0 to x of f of t dt. Based off of this, we want the third degree Taylor polynomial for g at x equals 0. So essentially looking for a Maclaurin series for our g function. Well, g is based off of f. So before we can figure out g, we need to write some kind of polynomial to represent f. And because we want a third degree Taylor polynomial for g, that means we need to go out to at least 2 degrees for f. But they've given us enough information, I'll just go out all the way on it. So f, using our Taylor formula here, is just going to be f of 0, which is 3. And I'm going to say f of x is approximately equal to this because we don't have an infinite series here. We're just cutting it off at 3 derivatives. Next, I'm going to have f prime of 0 times x. So that's going to be negative 4x. Next, I'll have f double prime of 0 over 2 factorial. So that's 2 over 2 factorial, and we have an x squared there as well. And finally, I don't really have to go out one more, but I'm going to. We're going to have f triple prime over 3 factorial times x cubed. So that's 1 over 3 factorial x cubed. All right, now I need to take an integral of this thing. But before I do that, I'm actually going to simplify this just a little bit to make my life easier. So I've got 3 minus 4x plus, this is just going to be x squared, and then this will be 1 over 6 x cubed. All right, let's go through now and take the antiderivative of this thing. Now, this is actually a definite integral from 0 to x, but because I'm plugging in 0 as my lower limit of integration, and when I take these antiderivatives here, I'm going to have all x terms, everything is going to zero out when I actually plug in 0. So I'm not going to bother putting stuff inside the evaluation box. I'm just going to go straight to taking my antiderivative with x's. So this first one is going to be 3x minus, this bumps up to a 2 for the power. Dividing by that, we've got negative 2x squared. Then this bumps up to a 3, so this is 1 over 3x cubed. And this one, oh, wait a sec, they just want third degree Taylor polynomial. We've got 3 degrees right here. So we're actually going to stop and look at the answer choices now. And it looks like, let's see, we need a 3x minus a 2x squared plus a 1/3 x cubed. That looks like choice C. So there we go. For number 12, we've got a big open response problem here. So they're giving us this logistic differential equation up here. And y equals f of t is the particular solution with f of 0 equal to 8. which may or may not be important for this particular part of the problem. For part A, we have a slope field for this differential equation. Well, that was nice of them to give us that. They want us to sketch possible solution curves through the points 3, 2, which they've labeled right here, and the point 0, 8, which they also gave us a dot for. So to do these solution curves, you basically have to follow the tangent lines through the point that they gave you, and just make sure you keep following those tangent lines. So we have this dot. To get there, we have to follow maybe these tangent lines, and then we're just going to follow them up through to this horizontal asymptote, like so. So there we go. It's about as good as it's going to get. And then for our other solution curve through 0, 8, we have to come down through here and approach but not touch that horizontal asymptote. So these both would have gotten full credit on the AP exam for following tangent lines and going through those points. For part B, using Euler's method, starting at t equals 0 with 2 steps of equal size, we want to approximate f of 1. So we're given that f of 0 was 8. That was our starting point for approximating f of 1. We're going to have to do this in 2 steps, so we're first going to have to approximate f of 1/2, and then we'll have to use that to approximate f of 1. So let's start with f of 1/2. So f of 1/2, that's going to be f of 0 plus the derivative of f at 0 times our step size of 1/2. And it's going to be approximately this. So f of 0 we know is 8. Now we have to find f prime of 0. We have a differential equation up here that we could use to find slopes. The trick on this one is that we have y as kind of the input to this, not x. So I'm not actually plugging in 0 up here. I'm plugging in the y value when x equals 0. Do we know the y value when x is 0? Well, we do. F of 0, they told us, is 8. So when I'm doing f prime of 0, what I'm really doing is 8 divided by 8 times 6 minus 8. So that's just 1 times -2, which is just -2. Plugging things back in now, we can say that f of 1/2 equals, or is approximately equal to 8 minus 2 times 1/2. So that's just going to be 8 minus 1, which is 7. All right, for our next step, we need to calculate f of 1. We're going to do that by taking f of 1/2 that we just found and adding the derivative at 1/2 times the step size of 1/2. So here's the setup for our next step. We have the number that we just found. This was f of 1/2 approximately. And again, we're taking the derivative at the new x value times the step size. So what's the derivative at 1/2? Well, we're going to again have to plug in the y value wherever this x value is. What's the y value that we have to plug in from 1/2? We found right here that f of 1/2 equals approximately 7. So if I'm doing f prime of 1/2, I have to use this 7 for my y value in the differential equation. So that's going to be 7 over 8 times 6 minus 7, which comes out to just -7/8. So then I can rewrite this as 7 minus 7/8 times 1/2. This is numerically equivalent to whatever answer they wanted. So we're actually done if this is an AP free response problem, and it is. Or if you want to show off your fraction skills, you can keep going and risk losing the point. But let's show off our fraction skills here. So this is really 7 minus 7/16. So that's really 6 and 9/16. 6/16 is 96/16, plus another 9 is going to be 105/16 if you really have to simplify it. But you don't. For this part of the problem, they want us to write the second degree Taylor polynomial for f about t equals 0, and then use it to approximate f of 1. So my general setup here, I'm going to have f of 0 plus f prime of 0 times t. And then to get the second degree polynomial, I need one more. So I'll have f double prime of 0 over 2, or 2 factorial, times t squared. So this is my general setup. I'm going to start plugging some things in now. F of 0 we actually already know. That's 8. And f prime of 0 we actually found on part B. That was -2. So I can already write -2t. But this last part is kind of our sticking point here. We need to find f double prime of 0. Okay, well, For that, we're going to have to go back to our differential equation and take the second derivative of this thing. So for that, I'm going to need, based on what's going on here, the product rule. Or at least that's one way to do it. You actually could distribute y over 8 and use the power rule, but I'm going to go product rule on this one. So let me set up my box and ribbon. So I've got, let's see here, y over 8, or 1/8 y, either way. And then we've got 6 minus y is the other thing. So these give me derivatives of just 1/8 dy over dt. And this is just going to be negative dy over dt. So not that bad to deal with. So now if we have a y value of 8, because that's the y value at x equals 0, and if we also have a first derivative of negative 2, which again we found that in part B, then the following is true. Setting up my box again, this is going to be 1/8 times 8, which is just 1. Over here we've got 6 minus 8, which is negative 2. Down here, this is 1/8 times negative 2, so negative 1/4. And this is negative negative 2, which gives us positive 2 over here. Now doing my ribbon to multiply these together, I can say the second derivative at 0, 8 is going to be negative 1/4 times negative 2 plus 1 times 2. So this is going to be, let's see here, positive 1/2 plus 2 is going to be positive 5/2. So then plugging 5/2 in for f double prime of 0, I've got 5/2 over 2. Careful, there's still a 2 down here. So that's really actually 5/4 if I divide 5/2 by 2. So then I've got 5/4 t squared. And I'm not quite done here because they wanted me to approximate f of 1 using this polynomial. So I can say f of 1 is approximately equal to 8 minus 2 times 1 plus 5/4 times 1 squared. And I've got all constants, so I'm actually done. But if I wanted to simplify this, this is going to be, let's see, 6 plus 5/4. So that's going to be 24/4 plus 5/4 is 29/4. For part D, they're asking for the range of f for t greater than or equal to 0. So this one's kind of tricky because it comes at the end of this problem. It would actually be very helpful to look back at part A where you made this handy-dandy solution curve for f. Now there were two curves on here. The one that goes with the f that they're talking about is this top curve. They told us f of 0 equals 8. So this is the curve that went through the point 0, 8, and this is the only curve we look at when we're figuring out the range of f. The range is just all the y values, and they're asking only about y values where t is greater than or equal to 0. Well, that means we're taking a look at just this piece of the graph from the y-axis onward. Now, where are the y values? Well, we're at exactly 8 here, and we can't go any higher because we'd have to go before the y-axis. And as we move to the right, we have this horizontal asymptote, and we can't get any lower than 6. We can't actually get to 6, but we can get pretty close. So using our slope field, since f of 0 is 8, and there's a horizontal asymptote at y equals 6, we can say our range is going to be 6 less than y, because we can't get exactly to the 6, but less than or equal to 8, because our curve actually does go through 8 at the t value 0.